and thanks for having me here. It's always fun to come here and talk to people at Queen Mary and seeing lots of good colleagues around. This is a kind of I'll try to keep it short, 35 minutes talk, and we can have a discussion. It's not a big study, it's not a keynote speech, it's just one meta-analysis, a bit of a critical reflection of the field. So kind of small recent study. I think this was submitted 5 weeks ago to a journal, so I don't know when it goes through. And anyway, so it's fresh work. But anyway, let me start by just, I think Harris can recap, but I mainly work on music and motion, but there's some new ideas there, new theory and so on. But I seem to be, as I get older, I seem to be doing more like meta science of my own discipline, music psychology as well. So there's more. I'll be looking at the transparency of my field, music psychology, by looking at all the journals or the publication of journals. How weird, how Western-oriented is this field with Kelly Chaplowski and others, or gender distribution. So a bit of like a self-reflection at this stage, like what is this field? How balanced, how vital, how biased are we in music psychology? And I also like to keep my old topics in music perception going on, but that's a different kettle of fish. And as alluded, there's a small but fun little lab, music and science lab at Durham. We kind of focus on different topics. About 10 people, 12, few postdocs, couple of staff members, PhD students, and that photo is literally 10 meters from the lab door, and it's actually on the UNESCO World Heritage Site in front of this cathedral, 900-year-old cathedral. So not the most high-tech location for a music and science lab, but it makes a good contrast for when you come into the lab. Anyway, that's where we are in the cold north. Anyway, going back to the topic, a meta-analysis of computational recognition of emotion in music. And to start this, I'll just kind of, maybe there's already people who are converted to music and emotion. It's a wonderful topic, but I just kind of start with like saying that, let me just try to get this. Can I move these out of the way? Well, I'd say music and emotion is kind of thriving topic. I mean, if you look at look at Web of Science keywords of any affect term and music, it doesn't show any sign of flatlining or abating. It's like going linearly increasing the number of studies, and the topic seems to be quite interesting. But what's more interesting is the maybe division of the scholarship areas, the kind of disciplines, the wide areas where the studies for the last 15 years have been done. And you could say that engineering and computer science is about a third of music and emotional studies. Neuroscience and psychology is another third of the music and emotional studies. Arts and humanities tend to be a minority nowadays. And then there's a medicine type of studies. I'm kind of interested now in the kind of psychology and computer science kind of a section of this. So I'll kind of talk more about the emotion recognition as models that come from computer science, but also what are we actually trying to measure with these models. So I kind of try to combine the computer science and psychology, although I do come from the psychology background, so I don't have any credentials in the computer science. And let me try to, I think we are kind of a little bit blocked by this. Sorry, I can't see my cursor, so I can't hit OK. Okay, can I reshare this? Move this to somewhere else. Yes. Better. A little bit better, yeah. Anyway, so when I'm talking about the computational models, I kind of just want to remind you all that we have computational models for different reasons. We might be doing them for explanatory reasons to understand, I mean, for emotion recognition, we want to sort of understand how music may be able to carry some kind of information that's relevant for emotional communication. And that's, should be theory-driven, should lead to very much interpretable models. And that's really what music psychology is doing. But you can also have complete different, well, not complete, but you have different aims. You can build predictive models, try to just get best prediction from audio, and it doesn't have to be theory-driven. It doesn't need to lead to an explanation how we as humans do it. It can just lead to a very good models, which are useful for recommendation or applications and so on. And of course, this is the other part, MIR or computer science or engineering might be doing that. And of course, the lines are a little bit more blurred, but these are the kind of a perspective that's good to keep in mind when we have different groups of people, different disciplines building these models. And this distinction will come clear later on. Okay, when people are building models that predict emotions, I mean, there are two different types of tasks. I mean, this is very simple, but you can build predictions of dimensions of emotions where schemes like arousal valence, affective circumflex model of emotions is being kind of predicted. So every music example might be projected on this low dimensional space, and the exact coordinates is kind of as a proxy of what kind of emotions are they expressing without labels. They are just labeled by the valence and arousal coordinates. There are other coordinate spaces of this as well. Anyway, and there are a lot of data sets out there which kind of contain pop music annotated on terms of valence arousal, energy arousal, and so on. The other thing is, of course, you can also predict emotion categories, maybe a bit more common. Actually, you either do kind of basic emotions, fear, happiness, sadness, anger. Tenderness is not a basic emotion, but this seems to be the case in many of the music studies. Or you can sort of, you can also kind of do valence or arousal quadrants, like the categorize these locations. Just talk about the upper right corner, the quadrant 1, which are like the high arousing positive examples and so on. So you kind of have a classification system that attempts to sort of describe in which quadrant these examples are in. And then again, you have lots of, I mean, there's more data sets, but it's just an example of recent ones. There's plenty of these data sets out there that have, again, mainly pop music, but other examples as well. There's more than 20 different datasets containing, mainly following either two of these tasks. Anyway, just to give you kind of the basics where we're going. If we kind of if I would have to summarize how well this task is being done, how good are the models? Bit of a context of that, of history. So let me put just some markers on the table. Katayoshi started this in the late 80s, having a kind of a audio-driven model to sort of describe some kind of sentiments. Patrick Ustlin in the late 90s kind of built some audio-driven explanations of expressed performances. Not really a model, but regression models of acoustic features. Eric Jan did a very influential model of linear regression of large datasets at the time, pop music. I put myself there for selfish reasons. That was the first time somebody did like 9 different datasets in the one study, kind of applying different genres to it. Much more challenging task. Alinaki put a landmark on assessing the qualities of the datasets and so on. So the history has been first very simple linear models, then more machine learning, really diverse set of different models, support record machines, and then it's more deep learning later on. But still, the answer, how good are these models, is actually really, really difficult to answer because the models are not compatible, the outcomes are not compatible, the metrics are not comparable, the datasets are kind of obsolete, or the tasks are different. So it's kind of difficult to compare how good are these models. Fortunately, we have had some tasks. I mean, we can say Mirex audio mood classification task was kind of launched in 2007 the first time, with a kind of funky 5 different categories to predict. And it reached 53% accuracy on that year. And then it sort of went on, and 10 years later, it had reached a level of almost 70% of accuracy on this task, and then hasn't been continued as such. So that's the only benchmark that we have right at the moment, maybe. So it's actually kind of interesting and kind of embarrassing, at least to my view, that we actually can't really say how good are these models. So that kind of led to a simple observation that, okay, we need to know this. We need to know. I mean, I should be able to tell a funder and tell everybody that, what can we do with these models? So we came up with a meta-analysis plan. We pre-registered that a year ago, kind of planned what we do. You can read it online, and then started to so meta-analysis is studies of studies. So we kind of look at existing studies. We don't do a study of our own. The latest model, we look at pool the evidence from existing papers. That's the idea. So we kind of concentrate ourselves to last 10 years. Not to make it a history project, the last 10 years, and kind of pull together studies from Web of Science, Scopus, and OpenAlex. We had about 500 studies to start with. Many of them were not really doing the things that we were expecting them to do. We kind of filled down this to about 100 studies that we had to read, properly annotate every modeling decision, every stimulus decision, and so on. And then we kind of realized that many of them don't actually have the qualities for the meta-analysis. They don't have the details. So it sort of became a bit slimmer. So half of them were discarded. So we ended up having 46. And when we're coding all these 46 studies, we kind of realized that some of them are just has to be excluded for some serious quality concerns. And I'll talk about the quality concerns later on. There are some not proud moments in this study. So we had to bin few more. So we ended up having only 34 studies, which is a bit less than I kind of hoped to get after seeing so many of these studies being published. Anyway, that's still a decent starting point, and give you an idea of the shape and the size of the data contained in these papers. The average stimulus number these studies were building the models on was like 300. The median is 303. Smallest study used only 20 excerpts, and the largest study in terms of stimulus number used 5,192 excerpts. And you can kind of guess that the music psychology studies tend to have like less. The minimum example is per episode notes from 2018. The model is built on with 20 examples. You might be in disbelief that how can you build a model with 20 examples? And the largest examples are from deep learning model computer science. In terms of features, these studies tend to use kind of fairly large number of features on average. I mean, the median 653 features. So people just feed in whatever. If you know your statistics, you are kind of a little bit concerned at this point. Well, how can you know that stimulus amounts are quite small? How can you feed in? Anyway, deep learning is kind of doing a bit of heavy lifting here, but in terms of, there are some studies which have only like 3 features. Again, Mike Schutz, McMaster study using kind of predefined theory-driven features to something quite crazy. Zhang using 14,000 features. Quite a large diversity in terms of what modeling contains. Classification, those studies which were about classification, they typically were 4 classes to predict quadrants, 5 basic emotions, 6 variants of basic emotions, sometimes even 2. And I'll talk about those options later on. And there were 290 models reported in all these studies. So quite often studies report 3 to 15 models. They have the baseline model, they have some alternatives, they have their latest, whatever they propose, and so on. So lots of models. Yeah, Marcus.
Is more categorical classification rather than linear?
Both. I'll kind of split them. I'll kind of do both linear or the prediction of the valence, arousal, and classification. They're all now contained in the same kind of bucket. I'll report them separately because different modeling. So the model techniques that people were using these, we kind of simplified reporting of this. So we kind of classified these into 4 different broad categories: linear methods, neural nets, neural networks, support vector machines, tree-based methods. And of course, you have lots of variance within there. And you might sometimes may disagree on our classification, but this is just kind of for us simplifying the kind of the largest number of model architectures there are. But I mean, you see quite a lot of different, probably familiar techniques being used. In terms of how popular these techniques are in this type of modeling, it's fairly surprising that the first 3 linear neural nets and support vector machines were almost like equally popular. The tree-based methods, random forest and variance were not as popular, but that's the kind of reality what we see people trying. And of course, people might try different kind of architectures in the same study. When I'm moving to the results, you want to know about the results. These are just like what the data looks like. When I summarize the results, I could summarize across 290 different models, but we want to give a positive spin to the results by choosing the best model out of each study, because the baseline models are kind of poor. So if I use the average of all the models in the paper, everything gets kind of diminished. We have done that. Our manuscript contains comparison with using old models, and tends to be like a little bit more modest. Not that much actually, but it's clear that when we represent these studies, we kind of put their best model forward as an outcome. We also kind of converted everything into compatible metrics, correlation coefficient for the Valence arousal and Matthews correlation coefficients for the classification studies, which is much better than your F1 precision and so on. Anyway, I'll talk about that later on. And then we did a random effects meta-analysis modeling of this. Okay, so you want to know how good are these models? Let's start with the arousal prediction first, because that's the easiest. It's known to be quite capable for years and years, so it shouldn't be too difficult. And then we move on to valence, which is much more difficult, and classification should be also quite good. Anyway, looking at the results, this is a kind of classic way of visualizing meta-analysis results. Forest plot on the right, where you see kind of everything being converted to the same metric, correlation coefficient here, and you see studies. So in the left-hand column, you have the study, the author names, years. The L is kind of number of stimuli the study use, and the R is the correlation coefficients obtained in this, the best model. And you see arousal prediction tends to be fairly strong, so correlation of 81. There's models that are much stronger, so above 90s even. Quite a consistent patterning. There seem to be like four papers or 4 models that actually don't really nail this task, which is quite surprising. Quite surprising that we know that this is quite easy to predict from audio, but still quite modest for some studies. Anyway, I think the pattern is mainly pretty clear. It's not really surprising. It's nice to see kind of concrete number after kind of seeing just individual studies and not being able to compare them. So I'm not surprised. I was expecting something like this, but I don't know. I wasn't expecting a flurry of poor studies coming through the years recently. But anyway, that's what we have. If I split this down into maybe techniques, if I look at some of the techniques, kind of see whether techniques make any difference. There's not huge much of a difference. There's a linear methods tend to sort of provide overall better outcomes than the other techniques. Maybe that's a kind of a quick summary of this. If we split them based on how many features they have, we kind of analyzed studies that had more than 300 features compared to those who had like moderate amount of features, 300 features or under 30 features. That seemed to be kind of indicating that, yes, well, smaller amount of features tend to sort of do slightly better. But these differences are actually really mild in the I think statistics are actually hidden behind the Zoom bar, but these are borderline significant internally. So not really clear picture. Maybe we are kind of doing so well already here. If we turn our attention to valence, which is a much more difficult task, because I mean, kind of defining what's positive, what's negative, it tends to be a bit more culturally attributed. It's not so clearly embedded in the musical signal, I would argue. And this is a horrible picture now. I mean, that forest plot shows us a wide heterogeneity, I mean, wide diversity in the results. The results are much poorer, correlation of 0.67, but you can see that there's almost half the studies are all over the place, like actually quite poor. And
sorry, can I quickly start?
yeah, please do.
These are the results from the papers themselves. You did not rerun all.
No. We took the the model outcome, converted it into the same metric, and of course the stimulus number is part of this. How solid is the information? But we couldn't have done that because many of the models are not, available. They are not. I'll come back to that. So that would have limited us from 30 studies to probably like 13 studies where we could actually run the models. That would be a very small subset. So, I mean, this is the method, the way you get the outputs of these, and you trust that this is the the cross-validation and everything is done properly. Anyway, I'll kind of I reflect on that. That's a good point. But no, we didn't run these models. This is not the implementation error from our. That's that outcome number in, let's say, the worst paper, Koch and others. They might have used R-squared number there, but that's the number that you can get from them. Small number of stimuli, so the error bars is wider and so on. Anyway, so valence very clearly, if I summarize, I mean, this is not a case closed, or we can't really model valence in a satisfactory way. If you think of 67 correlation of 0.67, that's kind of in terms of R-squared, that's kind of 45. That's less than half explained with anything that you can throw to it. So there seems to be something quite challenging going in the valence, at least. Okay, and I think the same story that if you look at the model techniques, linear methods, any variant of linear methods seem to be doing, it's more natural for this times top, so they tend to dominate. Although none of these differences actually are significant, they are just illustrative for your purposes, but because there's so much variance in this data for valence models, the differences are kind of meaningless. Same for the features. We see differences, but the models are all over the place, so the statistics don't bear it out. Anyway, moving on to classification, then we kind of I'll reflect more about. So classification, I kind of presume that this would be fairly solid, and this is now using the Matthews correlation coefficient, which is almost like correlation coefficients from -1 to +1. a bit more robust version of the classification metric. And you can get as a summary, most of the classification studies do, I would say, a fairly good job. If you bear in mind, this is a subjective task, this is emotion attribution, emotion annotation, where there's still leeway and people are not always agreeing what the labels mean. So you get on average classification accuracy of 87, and you get 5-6 studies which are higher than that, above 90. You could say that it's fairly at a high level, considering that this task tends to be there's subjective variance always in this topic area. So kind of a fairly happy. I think there's improvements to be kind of obtained in the future years, but it's not a mess in comparison to Valence, for example. Okay. Prediction for the audience. So if we kind of looked at the journals where these were published, journal attributions in Scopus or Web of Science, and kind of attributed that half the Valence arousal studies were published in psychology journals, half of them, a little bit more than half of them in engineering journals. So which ones are the better? So think of collapsing across. So which discipline is doing these better, higher prediction rates? Hands up who thinks engineering will this, hands down. We are in the minority. Okay. Well, we both win because this is a draw. There's no difference between how these fields actually operate. Yeah, there's always a random variation. There's a random variation, but I wouldn't, coming from psychology, I wouldn't take this as a win. It's actually we actually wrote into the meta-analysis pre-regression report. We kind of expect there to be a small difference between model success and model interpretability, favoring engineering actually for model prediction rates. But it's a draw so far. Let's wait for 5 years and reanalyze, and maybe there's a difference. Anyway, competition is on. Right. So if I try to summarize, I mean, this is kind of little neat study, very self-contained, and if I summarize, we can kind of get decent or good prediction rates from audio for arousal, but really poor, quite mediocre or poor, I would say, for Valence. Classification success is excellent. I think there's still room to be improved, but considering that we as annotators or humans don't always agree on these, I think we are getting close to something that is the upper limit of these the performances. But what was really kind of made us to struggle and kind of realize that there's such a huge diversity of quality across studies. We were surprised about that, and we also noticed a lot of lack of transparency and quality control, which I want to kind of talk to you more about and try to kind of understand where these issues come from. So let me move quickly. I'm going to give credits to the co-author, Cameron Anderson. He was visiting Durham last year, and a PhD student in McMaster. Very nice guy, and really capable. The whole project was made in GitHub, so everything from pre-registration to preprint and data analysis and scripts are in the GitHub. So if you want to go dig deeper and see your favorite model, go there and dig it up. It's all there. Anyway, I want to sort of have a bit of a short reflection of what we kind of realized when going through these studies and the bigger pool of studies that we kind of discarded. Kind of a little bit shocked us, and I think that's the kind of message that I want to kind of give, that we need to kind of focus on what we are doing, because there were so many critical issues that were kind of considered or not considered. And if I start with some kind of conceptual, like really broad conceptual issues, really briefly, many of these studies actually don't really use the theories correctly. It's, you might have like a, they might talk about affective circumflex, which is a theory, dimensional theory of how you can map emotions on nuanced linear dimensions, and then they go and measure categories of these quadrants. That's not really that's not really compatible with the theory. So it's kind of difficult to know what's the thought process behind this. There were some even worse implementations, like mixing felt emotions and perceived emotions. So if you use like something like GEMS, which is designed for induced emotions, and if you try to do that for the perception, it's not really what it's meant for. So it's not the greatest reading of the literature, I would say. So I think that kind of theory warning needs to be there, that if you use a concept, read about the concept and use it in a proper way. Datasets were always not really capturing the emotions reliably. So normally you have an annotation. You have people to rate these emotions or annotate these classes of emotions, but you also have like indirect. You might have like tags, which are kind of derived, or you might use a dictionary for tags to sort of convert these into valence, arousal, or the quadrants. And in these cases, we really don't know whether we are talking about the emotions or something else. So there's a bit of a caveat there. And also, in some cases, the targets what people are trying to predict, maybe not the most relevant ones. And it's a good question, because if you ask people what music may express, or what emotions can music express, you get something like this. These are the results from many years ago, 20 years ago. Patrick Usley did a survey of Swedes in Sweden. Lay people said, well, music can express longing, love, anger, joy, and there were 80 different, but these were the top from the top 9 selection from top 9. And actually, you don't see these. You see some of these joy and anger and sadness sometimes, but longing, solemnity, love, or being in love. I mean, no one has ever done any work on these. So it's kind of surprising that we are kind of focused on something, that we inherit the frameworks on something else, but we are might not be the relevant stuff. We recently tried to sort of like update this Patrick Usley study by making an iterative paradigm where we kind of offered participants, crowdsourced participants, all the possible affect terms. I mean, more than 600 terms. And they could also link these to the music examples and kind of contextualize them in certain activities. And we had like quite many iterations over 3 experiments. More than 5,000 people were saying these are the relevant expressed emotions in music. So we kind of dug into this, went for this structure discovery, and what came out, it's a long story, you can read that from the +1 paper, but it was not valence arousal, and it was not basic emotions. Let me say that, this is kind of, we came up with something else. I mean, other participants came up with something else. And it's not actually too far away from, I mean, these are just some of the highlights from that. It's not really the structure. These are just bubbles, but, in love, I mean, in love is an example that the Swedes were saying 20 years ago. Being in love is something that music seems to be able to express, but no one had ever studied, which is kind of surprising. Most common topic of music. Romantic is not really, I mean, you can argue that it might be captured by valence, arousal, some quadrants, but not really. There are so many other qualities there. So I'm just putting it out there that, if we think about what we are modeling, we might have to kind of reshift our attention to something that is more valuable for us as listeners. And just to point out that whatever we found, these are never featured in music emotional recognition studies. Anyway, the quality critique is maybe a bit more hilarious, a bit more fun story to portray pretty quickly. There were some meaningless models. I'll give you an example of meaningless model. There were some models that were classifying this, so high arousal, low arousal. So and they were really good, 96% classification accuracy. So you have a model that from audio is being able to say, is this above mean in arousal? Kind of useless. I mean, great for success. I mean, you report a model that, we nailed it. We can predict 96%, but, as an explanation, what is this music representing? If is it above the halfway line or not? It doesn't have any meaning to it. Yeah.
So in the meta plot that you showed, that 96 is represented that way.
Yeah. Yeah. So
this was one of the studies you included?
Yes.
Yeah. So there must have been some really bad ones you. Excellent.
Yeah, this is not the bad ones. I mean, this is kind of borderline, but
Was it?
Maybe I can't remember, but maybe I'm declined to memorize right now. Attribute that. Anyway, I'll give you sort of like maybe another one. Like there were studies that kind of looked really odd, really bad, and there were many of. I'll name and shame one journal, for example. We look at quite a number of papers from mathematical problems in engineering, and while we were doing this last time, we started this last July. We kind of noticed that some of the papers were retracted. I mean, not these papers, but other papers so 17 papers from that journal only were retracted during the last summer. So we kind of thought, crash journal, let's bin everything that is in that journal. We can't trust any of this. So I mean, I've never been reading studies which are so poor. So it was like not the most inspiring reading experience. You read you're reading the last 10 years of all these wonderful modeling studies, and then half the stuff that you read is like, who writes this or articles? These are questionable quality. So we had to bin, and I think we have actually put like on our GitHub elimination comments. There's a bit more fun story there why we had to disclose a reason for every study that we kind of binned. Anyway, lots of questionable qualities in the papers themselves, and of course there was a lot of inconsistencies in the metrics. And I know that you guys might love your F1 scores and area under the curve and recall and all of these stable classification metrics, for instance. But I would encourage you to kind of look up Matthews correlation coefficients. I mean, biosciences have converted from F1 to MCC. It's more robust for unbalanced classification. It's more expandable to multiple categories, and it has other positive properties. So some of the fields are kind of converting to MCCs. It would make our life easy as well. Regression, you might go for this kind of error, root mean square error or mean absolute error, which are of course from 0 to infinity. You really don't know what they mean unless you know whole variance of the study. So I mean, we are not very happy to sort of code these. We actually don't learn. We can't compare between studies unless you. But if you use a old familiar R squared, you actually can't compare directly. And of course, you can adjust this by number features and so on. But anyway, these are small things that kind of makes life a little bit easier if we kind of start to keep track on what people are doing. And I think comparability across studies is something that should now be a top priority, because there'll be just these singular studies that are not very meaningful on their own. Kind of wrapping up, but we also find that not all the details were kind of given in many cases. I mean, a bit disappointing that stimulus details and feature extraction and transformations and whatever the model tunings were quite often hidden away. You just get the feeling that there's some kind of modeling. There's probably some kind of overfitting going on, but we are not told for the full details. So, and about the 20% of the data was shared if they use common data sets. Code wasn't always available, quite actually seldom available. which is surprising because I think you all been taught to do that. But I think these, and you are in a good company, because if you look at the more kind of music psychology don't share data. Exceptional people like Marcus and me and Peter Harrison and a few others, we always share data, but we don't make a dent on these numbers. we are the 2.5%. Psychology tends to be a little bit ahead. These are based on analysis of samples of journal articles for the last 7 years, looking at how many of the music psychology studies share data and how many of them share code. And it's the transparency of these fields is not really yet there quite, and that's a limitation as well. And finally, I kind of also need to mention the lack of diversity. I mean, these were nearly all Western pop. I mean, we understand now something about the Western pop, emotions in Western pop music. There were 7 exceptions, 5 Chinese music sets, 1 Turkish traditional, 1 Hindi classical music. I can't remember. Anyway, so as Georgina Bourne, I know that she has a seminar series, and you talk about the diversity and all of that in Queen Mary, but I think it's a message that needs to be repeated time and time again, that we really need to understand whose emotion attributions, whose music, and I don't think we really nail this topic if we just focus on most commercially available. I think we need sort of we don't need to do full global studies. I mean, those are nice as well. We can also kind of dig into subcultures and learn a lot of regional varieties. So we can kind of go native. We can kind of dig deeper in the Western cultures as well. So that's a bit of a critique. And I mean, same thing happens in psychology. Music psychology has been completely focused on Western authors, Western stimuli, Western participants. There's about 6% is like more diverse than that. So we are all in the same company. We all need to kind of diversify our actions if we want to sort of get a bit more wider understanding of the topic. So to summarize, well, it's a bit trivial statement, but we can do kind of these in computational models, and we can kind of now infer that in arousal prediction we are kind of hitting somewhere explaining 65% or 66% of the variance overall if we kind of aggregate the last 10 years from the meta-analysis. So there's a bit of a progress going on. If we kind of interpolate from the Mirex audio music classification of different metrics, but anyway, so the classification accuracy has kind of steadily also increased. So it's a steady progress, and I kind of expect little improvements over the next 5 years as well. But I think we need to also say that we are not really capable of doing valence, for example. That's like so clear. It's unresolved. It's culturally attributed. There needs to be something else than the audio signal to be able to solve that. I think that's good. I already had a rant about the Western pop focus, and how while we get great models, maybe we need to actually kind of rethink what we are targeting when building these models. I think we are kind of not doing the best set of emotions in every time. And I didn't really mention this, but I think that if you compare any to other domains of modeling, visual stuff, images, pictures, even speech, I mean, music tends to have like small datasets, and that's because it's expensive, it's resource intense to create these annotated datasets. So, but I think that's now the current limitation for really applying resource-hungry deep learning, and I think we need to sort of have a few discussions of how do we expand these datasets and how do we make them a bit more relevant and contextualized. Anyway, I think that's small study of the last 10 years of music emotion recognition, and I hope you found it at least entertaining, if not informative. Happy to have a discussion or take some proposals from the audience.